Hello and welcome back to the Scrap Mechanic CPU building series. If you have not seen the previous episodes in this series, watch them now and come back later. Anyway, in this video, we will discuss the CPU parts and how they interconnect. Previously discussed in this series is the RAM, but as you know, there are more parts to a CPU than just the system memory. I previously discussed some of the mathematical operations the CPU can do, such as addition, inversion, and bit shifting. The actual operations of the CPU take place on the part that I call the chip. Today I will discuss the other parts of the CPU according to how I built them. Parts of the CPU that have been covered are the chip and the RAM. But next, we will be talking about the spooler. The spooler is the thing that takes the code from where it's at and gives it to the chip. The spooler will also process system interrupts and jump commands. It can be called the CPU clock because real CPUs, this part of the CPU also determines what happens at what time. I mentioned that the spooler gets the code, but where does it get it from, you might be asking. That's where this next part comes in. The ROM, or read-only memory, is the thing that stores the code in a read-only location. An advantage of this configuration is that the code is hardwired and pre-installed. Code can also be stored in the RAM, but for sake of simplicity, I will be using the ROM in this example. So what you're seeing is the current 16-bit word length, 32-line ROM that I use. As you can see by these logic gates here, that function as pins, there's one input and one output. On any ROM, real or in Scrap Mechanic, there's an address which is sent from the CPU, and the information is sent back to the CPU with these pins. Now, these address pins go to a binary encoder, like you see here. And the output from each one, goes to the corresponding line of code. And once it allows the data above, through these logic gates, written on the wood with white paint is detected, to go through the sensors to these logic gates up front, and then these go directly to the output. Now that we have the ROM covered, it's time for the spooler. The spooler does a few different things: process system interrupts, process jump commands, and give the CPU code to execute. Today I won't be covering the part about system interrupts, as that will be in a future video. Now I will actually be building the spooler. So to start, I just have a simple wooden platform. Now on the front of this wooden platform is where the user will interact with it. Now, there's 2 buttons and a switch to start off with. This first one will be green, and this tells the CPU to send out the current address in the command it needs, and then it will get it back, send it to the CPU. And then when it comes back, if this next thing, the yellow switch, isn't turned on, it can't loop back around. And then lastly, this red button resets what line of code it's on, and also the code cache. This will all be discussed in a minute. Now it's time to actually start loading some things in, so that the spooler can do things. The first thing I have loaded in here is an adder. Now this is an 8-bit adder, because the CPU I'll be building can support up to 256 lines of code, 0 to 255. Now other CPUs may vary, and you, for example, may use a 16-bit adder because you have 16,000, I think it is, possible lines of code. So now I grab a weld tool and attach this right here. Simple like that. Now, this adder will be hardwired so that the first number on the addition is 1. Now, because of that, I'm deleting the first row of switches, and over here, I'm putting 2 logic gates, an AND gate connected to a NAND or NOR, I have NOR here, so that this one is always on. Now, I connect that to the rightmost one where that switch was, and you can see the output is 0. So if this was on an AND gate, like it will be, when it's allowed to output, the number outputted will be 1 more than the number that's put in. Now, where is this other number come from? You might be asking. Well, for that, I'm going to load in a 8-bit register here, and this will be this will be where it holds the number for the line of code it's currently on. Now, after distancing that a little bit away, here's that, and it has to be the same number of bits as the adder is, so that it can always have the same amount of lines of code. Now, next I'm going to remove the output here, and I'm going to, now these will be OR gates because it's something important coming later. But this row of AND gates, which is connected to this AND gate here, like I'm doing now, will allow the output to pass through to here, like this. All 8 of them. And the 9th, which is connected to the other 8, will also go to the allow write pin over here. So, now I need to connect the output from the adder to this. Now you might be asking, how do I know which one's the output? Well, the answer is it's connected to the lights on the back, which is this top corner one. That is on the adder I use. So simply, I just connect it up like this. And now, if I have a test button, like that, now it's output. Now, this will be not on a button, this will be on a standardized pulse length, as I'll discuss earlier. But the next thing to do is I need this this register here to go as the other input for the addition. Now, why it does this is so that when it needs to, it'll just add 1 to whatever line of code it's currently on so that it can go directly to the next one. So I connect it up just like this. So, now that that is done, you look and the adder has 2. And that's because it's hardwired to add 1 to whatever number's in the cache, which is also 1. So now if I press the button again, now 2 is in there, and 3, and then if I do it again, it'll logically be 4, as you might have expected. So, let me wipe that. But for purposes, I'm going to spawn in what I call a black circuit, which all it is, as I've discussed previously, which you should watch, is all it does is reset any logic gates, such as these ones, which flash when they're placed down. Right? So now, if I disconnect this, place it back down, see it flash, and then it stops. That's always useful when working with logic circuits like these type of storage gates. But, you know, there are other types, and you might be using them on your build if you are building it. So now, these lights aren't actually needed to stay, but something I like to do is I like to have a display out front so the user can see what line of code it's on. Right, so there's the 8. And then I connect the same output gates to these switches. Wait, correction. These do not go to the ones. It's the actual line of code that it's on that goes to the one. Wait. Where does that connect? Oh, okay, so that is the first one. That's the second. Now, these will show the user, who will be presumably in front of the CPU, what it is doing. As in, what line of code is it currently on? Now, as you see here, that is 0. But I go back and get a button, place the button here, increment it by 1, you see the user can now tell that the line of code is 1. So now it's time to get into what this green button does. So what I'm going to do is I'm going to build the port that it connects to the ROM with now. So that's 16 bits for the return of data, and then there's 8 for the address. Now, let me pull up the ROM real quick. This ROM only supports 6 bits of data, as you can see here, but that won't just be a problem. I just have to plug it in a bit differently. So, for simplicity, I'm just going to weld this on now and connect it up. And then, I also connect the rightmost to the rightmost on this because I have to squeeze as many in there as I can get. So, the one I have saved for the storage here, this register, conveniently has this logic gate here, which when enabled, allows the output to go through. Now, this should be directly connected to the ROM output, because it has to send out what number it's requesting. Now, even though this is on the leftmost, you look at it this way, it's the rightmost, which is 1. So, I gotta kind of flip it around here. Wait. Yeah, that's right, it's gotta be that one. So now, if I take my paint tool, like so, and I paint some data in white on line 1 as opposed to line 0, which line 0 is always being asked for and always being given back to it. Like, as you can see, if I put some data there, you can see it feeds back through. But if I hold down a button here, the data from line 1 goes through because line 1 is being requested. So, that's all good. Next, I'll be talking about how the button works. So, to start the CPU, one of the things you need to do after you flip the yellow switch, which I'll talk about why later, is you press the green button. But what does the button do? Well, first thing is it goes into what I call a pulse regulator, or as I used to call it, a buttons made good machine, because it makes buttons function well. So I connect it into the input on here, and I specify, let's say, maybe 9 ticks, right? And that with those 9 ticks, it goes to here to allow the number to be sent to the ROM. So you see that happens. Now, after that, you need to put timer, also coming from this output. Now, this will be somewhere from, 9 to 14 ticks, depending on how slow your ROM is and whether or not you're using RAM to hold the code. So, the next thing that needs to have is a 16-bit, or however many bits your instructions are, register, so that you can actually hold your code temporarily. So I weld it on just like that, and then always make sure to connect it to the black circuit, just like that. So when it's placed down, it can reset. And these bits will need to go from here into here. So I gotta remove these switches. And this button. So once that happens, also I'm just gonna put another logic gate here so that these all can be on the same time, and it will just go in. So after this timer, the 9 ticks, you need to tell it that it can write the data, but you also got to make sure that you have your data in order. So the leftmost bit on your ROM here should line up on here as the leftmost. So even though it appears to be the rightmost on here, all you gotta do is flip it around, and it's the leftmost again. This is so your code doesn't get to the CPU backwards and executes the wrong code. So, since the number 1 is in the cache that holds what line of code we're on, when the button is pressed, it should get the code from line 1 instead of line 0, which is currently displayed. That is, once I connect this up. Now, we can test it. But you see, that didn't work, did it? Or did it? I realized it didn't have anything on line 1. So, let's check it now. And look at that. The code from line 1 is pulled into here, which is great. Now, the next thing we gotta do is to build the pins to the chip itself. Now, these output ones will be useful, so I'll leave them on there. But I like to separate them in sections. So, because it's a 16-bit CPU, I like to separate it into 4, 6, and 6 sections, so that you can actually separate what command you're doing from the parameter. So simply I just connect them like that. Connect them. But then this gray logic gate, which will be enabled when it needs to go, needs to be on another pulse regulator. Because sometimes when troubleshooting, it's much easier to slide a timer than to place a bunch of logic gates for a pulse extension. So this gray one goes into the input, and the output goes onto what I call the command pin. Because some CPUs have a command on the number 0, and if you're sending all zeros, it won't know to do anything unless you have something that tells it what and when to do it. So after the data is sent in, it needs about 5 ticks of delay. You know, this timer tells it to write the data. It needs about 5 ticks of delay, and then it will tell it to send the data out. So now, when we press the green button, you see the data is sent through. However, this should probably be a higher number. I like to have it on somewhere around 15 ticks, because graphical computers are slower than real ones, as you might have expected. And you simply just can't have a short command. So the command is sent to the chip. The chip will do processing surrounding the command. Then what does it do? How does it know it's done? Well, quite simply, I call it the done pin. Now, like I did with the ROM, there'd be a whole duplicate of all these pins on the other side as well. While I'm at it, I'll add the pins for the jump command, even though I'll discuss that in a little bit. But those are important to have on the CPU as well. So, after the done pin happens, it needs to tell this gate right here, which again needs to be regulated pulse length. I think I have it on like 2, which, yeah, that's good. So that will go to this, which should be an OR gate, because sometimes there's multiple different things you need. So now I'm pretending to be the chip, and I just tell it that it's done. And look, it increments that, but then after it does that, which takes around, which we need to take the output, and that can take around 7 ticks, perhaps. We need to check if the yellow switch is enabled. Now, the yellow switch allows it to keep going after one command's done, so it can go to the next. So, if you unflip the yellow switch, all it does is pause it. And now, after it's done that, all we do is route it back to the same input as the green button. So now all I'm going to do is write code on here with the binary numbers to like 8. And now we can check if it worked. So, oh yeah, that's right. Next thing I need to tell you about is the red button. Now the red button just acts like a black circuit and resets all of the storage areas on here so that it can start from line 0 of code. So pull it in. There's number 1. Tell it that it's done. And then it sends out number 2. And I say, I'm done. 3, 4, 5, 6. You get the idea. It's working now. Now, this might actually be even faster on a real CPU. But let's say I turn off the yellow switch and I tell it I'm done. All it does is it increments it, but it doesn't tell it to go again. This is so that you can pause it, Now, let's say you have your CPU running and you need to stop it. You just unflip yellow and press red so that you're ready to start again. Now, that's code fetching covered. Now it's time to discuss jump commands. So one of the most necessary commands on a CPU is the jump command. Anybody who has ever coded anything will tell you that if statements are very important. No matter the command the CPU is running, if it needs to jump somewhere, it'll be through these pins here. They're 9 because it's 8 bits of addresses for possible code lines and 1 to tell it to go through. Now, what we need to do is if I'm the CPU and this is the tell it to do it command, and these are the 8 lines here, and I want to tell it to jump to line 1. Just like that. What it's got to do, also, button with these, is I need to wire these way back over to here and tell it to jump to 1, just like that. Now, it should only be possibly telling it to jump to 1, or whatever line you have, when it's ready. So now, if I'm the CPU, I just send it through like that, and look, it jumped to there. Look, it's supposed to connect up all 8 of them. Just like this. And now it's all ready. So, you can just run it like normal, but when the CPU sends a jump command, which could be with the if command or just a plain old jump command, it'll just send the new information to the line to do it. And that's why this is an adder, and not just like an incrementer where you press a button and it adds it by 1. It's because sometimes you have to tell it what number you want. And it can't just guess that. It has to actually calculate it. So, to recap what it does, what the spooler does, is you press the yellow switch to on, you press the green button, it fetches what should be the first line of code, and then it puts it back in that register, and then it comes back and increments it, and if the yellow switch is on, it keeps looping again. That's pretty simple. I hope you found this explanation of what a spooler is and how it works to be useful. If you have any questions or comments, feel free to let me know in the comment section below. Subscribe so you don't miss the next video, in which I will go more in depth on the instruction set of the CPU and the chip. Thanks for watching.